Yeah, all right, let's go ahead and get started. So Eileen said she'd be a bit late today. There's probably a few other people that might come in.
All right, before start.
All right, object-oriented programming. Who's excited? This is the class on classes. Okay, so what is object-oriented programming? The idea is to create an abstraction which encapsulates both data and behavior. Why you might want to do this is that the data model that you're creating might fit the real world better than other paradigms. So imagine digital twinning. There's this idea where you have physical objects and then you have objects in software that represent those physical objects. So this paradigm might work well for something like that. And then it also does provide considerable flexibility and extensibility through inheritance. We'll go over what that means in a moment. But I do want to have this warning here. Object-oriented programming, or the word object-oriented, is not synonymous with better. So just because you're writing a program doesn't mean it has to be object-oriented all the time. There's some people that think otherwise. Okay, so let's start with a conceptual framework, and I'm going to build this layer by layer so that we can understand what are classes, what is inheritance, and how it works. So we'll start with a simple dictionary. We define myDict, and we have two pieces of data in that, data 1 and data 2. So if we want to access data 1, we use these square brackets, and then in quotes, we'll have data 1. If we want to set a new piece of data into our dictionary, we just do the same thing, but we have a new key, and then we set it equal to the data, right? So everyone's seen this, right? Everyone's worked with dictionaries. Okay, so we're going to move beyond a dictionary into something that's called a namespace. And so Python provides a simple namespace in the types module, which is part of the standard library. So how you use the simple namespace is like this. Would say my namespace is equal to simple namespace, and then here we just define our data 1 and data 2. So that's pretty much the same thing we've done with this dictionary. All right, so we access the data rather than square brackets. We use the dot notation and then just the name of the piece of data we want to access. So this would have been the key in the dictionary, but we don't need the quotation marks now because it's assumed it would be a string or something that can be converted to a string. Same thing for setting data. Data 3 equals data 3. That's the same that we saw for the dictionary. And if you poke around enough in Python, you find out that actually everything, almost everything, is a dictionary or has a dictionary under the hood. So this my namespace underdict is going to be exactly the same as this dictionary over here. Okay, simple enough, right? So I'm going to visualize this namespace in this way. So each namespace will have the name at the top of this box, and then the data are going to be in the next segment, and any functions we attach to it are going to be in the third segment. I should mention we attached a function here to our namespace. There's nothing special about functions. We can add them into dictionaries as well as into namespaces. Okay, so now as part of this class, what we're going to do is define how these namespaces are linked together. And so formally, we're creating what's known as a DAG, or a directed acyclic graph, where we're linking this instance namespace. Now that got cut off a little bit. All right, so this says instance. We're linking the instance namespace with the class namespace, okay? And so what this linkage means is that if we look for something in the instance namespace and it's not there, it's going to follow this line and look for it in the namespaces that are attached to it. So if I said instance.classData1, what would this return? That's right. Yep, because instance doesn't have that, so it just looks here. Okay. Let's pretend like we know what these values are, because I guess this is building with two different versions of the software. So I could see it locally, can't see it now that it built and published. But anyway, I'll fix this later, so it'll be fine when you look at this. later on. But we have our instance namespace, we have our class 1 namespace, we have class 2 namespace. So it's the same concept, we're just extending it, okay? So if we do instance dot class 2 data, it's going to return whatever this is. But remember, this is directed. So if we do class 1 dot instance data, what would happen? Yeah, it's undefined, right? Technically, it'll raise an attribute error, but here you can't go backwards. Okay. Okay, so there's nothing special about the instances. We can have multiple instances, and they're isolated namespaces. So instance 1, instance 2, they don't interact with each other, but they do share the data in class 1 and class 2. Make sense? So if instance 1 has instance data equals to 10, and instance 2 has instance data equal to 12, if I look for instance data on instance 1, I'm going to get 10, whereas if I look for it on instance 2, I'd get 12. Does that make sense?
So what's the error in here? Because from class 1 to class 2, I can see that's class inheritance, right? But for instant to the error of instant to class, are you implies also inheritance subtitle?
So inheritance is going to be following these arrows.
Right.
Yeah.
But I never thought that instant, I never consider instant is an inheritance of a class.
Yeah.
We consider it's actually an instant.
So you're kind of getting ahead of me by one step here. We're still
okay.
just thinking about this DAG, but we'll see that this abstraction holds
Okay.
when we go to instances and classes. Yeah. Okay, and we can have the data named the same thing. So in this case, instance, class 1, and class 2 all have data attributes, but they have different values. So if we're looking for instance.data, it will return whatever value it has. Class 1.data returns what value it has, and so on. Make sense? Pretty simple, right?
Is there anyone online?
Eileen is usually doing that. So
I mean,
you want to log in?
yeah. So, but can you just tell me, because I put money on this. Hold on.
Okay. Okay, so let's keep going. Now, Eileen said she'd be here at past, so she'll pop in a few minutes. So this is extending the same conceptual framework. We have our instance, and then we have our class. So let's actually write this in Python. How we do that is we just define a class. So we call it class 1. We have our class data there. Here is a function that's associated with that class. And then there's another function called SumFunction. And so here, like I said, this is where we define the class and we attach the class data. This is actually where we're going to assign the data to the instance namespace. And by convention, we call that self. So when you see the word self in Python, you should be thinking instance. And then we have some function here. This is our behavior. So there is a special way that we're going to fetch the functions from the classes. So we'll modify our conceptual framework a little bit. And we'll say if we're going from an instance namespace and we're asking for not data, but for a function, what it's going to return isn't exactly that function. It's going to take that function and bind the instance namespace to the first parameter and then return whatever that is. Okay, so what that looks like is this. So we have class 1. Again, we attach our class data. This dunder init method, that's for creating instances. And then we have some method. So we'll start off by creating an instance that's going to be linked to this class namespace. It has data equals 42. And then when we call some method, automatically that first parameter is going to be the instance namespace. Again, we see self here. So think instance namespace. So yeah.
Stupid question.
No, go ahead.
On this notebook, where's the instance?
So I'm calling the instance self down here on line 10.
But you have defined the instance.
Yeah, this is creating the instance.
But the instant dot some instant. The line
Oh, yeah, sorry, that is a bug. That should be self. So previously I called it instance. I'll fix that. Yeah, thank you. So imagine it's either self or instance. These need to be the same. You're right. And so when we call it, again, it's passing in the namespace. And so when we call this, it's going to print 42 and 12. So it gets the instance namespace, grabs the data attribute, which we set up here in the init method, and then it prints data as well as whatever else we pass into it. Okay, so that's going to print 42 and 12. And actually, this is identical to doing it this way. We could, oh, there's another bug here. So we should say class1.sum method and then self and 12, and that would be the same as a line 11. So this is going to teach me not to modify the slides right before class. Okay, are there any questions on this, on how methods work?
So maybe it's good to just write what the correct one should be.
Yeah,
On the board,
let me do
because
that.
it's-
So we'll look at line 10. And instead of self, let's call this instance. That's going to be class 1. Open paren 42, close paren.
So if you change that self to instance, do you need to change two functions also?
It like
self inside.
line 7 and line 4.
Line 4.
No, we're going to leave that alone because that's convention. So whenever we have a function attached to a class, if it's a instance method, there are other types of methods we'll get to in a second. We name it self. Okay. So line 10 should be this, and line 12 should read class 1 dot some method. And then here, since we're using the name instance for our instance namespace, we pass in instance. And what? Okay, and these are identical statements. Cool. 11 and 12 are identical statements. Okay.
Why did we pass the instance in 11? Line 11?
Yeah.
Why did we pass the when we?
Why did we pass in instance as the first parameter like we're doing here? The reason is it's implicit, right? It's when we're calling some function that's attached to a class, instance namespace is already going to be down automatically.
So basically, if you call that function from an instance, you basically ignore the first
Exactly.
option.
You'll have-
You,
Yeah, and it doesn't have to be named self, it's just convention.
right.
But no matter what it is, the first parameter will always be named self, will always be the instance.
Yeah.
And then you can access the data you've stored in that instance.
And you can write the data.
You could also write it there, yeah.
Is the instant dot anything which you have like defined can be accessed through instant dot whatever you found in for data, right?
That's right. So anything you define in that under the method on lines 4 or 5, you can access that later on from anything that's like self. And so again, the idea is we're encapsulating the data, which we set in under init. You can really set it anywhere. It's best practice to try to limit it to just the initialization though. And then you access the data in other methods. Okay, so let's go through just a little bit of the nomenclature. So class or class definition, we kind of think of this as a blank form, right? We don't have an instance yet. The instance is the form when we fill in the data. Self is the conventional name for a class instance when you're defining what are known as methods or functions on classes. The call operator in Python, anything that has an open paren, closed paren, that's called call. So if we did instance open close, we would say that we're doing a call operator on instance or we're calling instance. Okay. Same thing for functions. If this was a normal function, we'd call that calling as well. Okay, attributes are accessed via getAttr. So instance data. This dot and then the name, we call that getAttr in Python. And we already talked about square brackets. That formally is known as getItem. So those are the names of those operators. An instance method we just talked about, the namespace for the instance will be bound as the first parameter for an instance method. However, there are other types of methods. There are class methods. And in this case, the class namespace is bound as the first parameter rather than the instance namespace. Okay. And then there's also static methods. And for static methods, we basically say we don't want you to bind anything to the first parameter. Just treat it like a normal function. So here's an example of a class method. In order to define that, we use the @ symbol and then class method. And that goes right above the function that we want to be a class method. And by convention, the first parameter name here will be CLS. We can't use class because that's a reserved keyword in Python for defining new classes. Okay, and so these class methods are useful for typically what are called alternative constructors. So in this case, I'm creating a dog with data from self.name. So I'm passing in the name to the dog to create that instance. But with this class method, we might want to read the name from a file. So how this looks, we have a dog named Maggie. That's my parents' dog. We can define it this way. And then that logic just goes through init. Or we can create a new dog from file. And we can either call this from Maggie or from dog. Those are exactly the same because it's a class method. Okay, any questions up to this point? Yeah.
So you need to be able to name which is inside this.
Exactly, yeah.
And the
It's gonna-
middle one is you will write Maggie in .name file.
Yep. That's right. So yeah, to be more clear here, so in this case, the logic is going to go through the init and not touch this from file class method at all. In these two cases, this is going to be called first. It's going to have access to this CLS namespace, the class namespace. It's going to open the file, read whatever name is in it, and then CLS.call or CLS call is going to go back through this init and return that instance.
Why there's a dog before open?
So this is a path object from pathlib. And there shouldn't be a space there.
Oh,
Yeah. Okay, so a static method. And I was trying to finish this before class, and so I didn't have anything more creative that dogs do. I don't know many dogs that add things together, but this is the example we have. So Maggie, we create Maggie again with by calling dog, passing in Maggie, but we can do Maggie.add, and then we'll pass argument 1 and 2. So notice that it doesn't matter if we're calling it from the instance namespace or the class namespace, it's going to be the same because we've told it that it's a static method. Now, some people think that there really isn't a legitimate purpose for this because it really doesn't have anything to do with the data that you've attached to either namespace. And I see that argument, but I think oftentimes it's good to group methods sort of conceptually. Like this has to do in some way with this class, so we can add it as a static method. Okay, so quick knowledge check here. We have a class called customer. Our data on the class namespace is going to be name equals default and bank equals Chase. Then we've defined our dunder init. We'll pass in name. And on the instance namespace, we're going to assign the name to the value name passed into this function. And then self.balance, we're going to set to 0. And then we have a method. What kind of method is this one? Class method, instance method, or static method? Instance method, right? And the hint is there's no decorator, there's no @ symbol above it. And then we're also using the word self. So you should be thinking instance method. So when we call that, we'll just lower the balance on the account. Now, of course, there's no way to have a positive balance here, so maybe it's like being in grad school, I guess. So start with line 1, Bob equals customer.bob. So what is Bob? An instance, perfect. Now I can assign a new variable to customer. So what is this? It's a class, yeah. So we just have another variable that's pointing to that same class namespace. And if I do bob.balance, what is this? It's not a method. It's an attribute. Yeah. So we're accessing the balance from the instance, right? So this should return 0. What about withdraw? Yeah, that's right. Okay, and then if we say bob.name, what value does that return? Bob, yes. Cust.name, what would that return?
Default.
Default, yes. So Hafiz, why default?
Because,
Right. And this isn't an instance, right? So we skip that node in our DAG. So we're basically starting here. We have no access to this namespace where we define Bob. Good. And then cust.bank. Chase, what about bob.bank? Did you already say that? Starting here, does Bob namespace have a bank? It doesn't. So it goes up here.
some of the bank isn't defined.
Exactly. Yeah. So where is it going to get a bank attribute? From the class. Yeah. So bank is up here. So when we say bob.bank, it's going to first look in this namespace. I don't have it. So let's follow this inheritance path. Formally, we're going to call this the MRO. I'll get into that in a second. So we follow it up and we do find a bank here. So that's what's returned. Okay, so classes in the wild. Some of you may not have a lot of experience with classes, but you've been using classes without even knowing it for probably years, as long as you've been programming in Python. Here's an example of NumPy. So we import NumPy, and then we're going to call this method, this function rather, which is going to create an array of random data. And this array is actually a class. It's an instance of a class. So it's the class is going to be numpy.ndArray, and the instance in this case is the name array. And if we want to check if an instance is an instance of some class, we have this method called isInstance, and that's built into Python. So this should return true. Or what assert does here is if the value that is to the right of it returns false, it's going to raise an exception and crash the program. If it's true, it's just going to pass. We'll get more into that when we cover testing. Okay, so here's something. Is this a method or an attribute? Method, right? And what about array.shape? Attribute. Yeah, so this is just a tuple of the length in each dimension for the array. Okay, so dunders. We've talked a little bit about dunders before. Let's look at some examples. And this one doesn't have anything to do with classes, but you should know about it because you'll see it quite a lot. And this is dunder name. Has anyone seen if dunder name equals dunder main? Jim, you've seen that. Anyone else? Okay. So the idea here is that this dunder name is set in every Python file. And when you run the file, if you run it as a script, it's going to have this value main. But if it's run as a module, that is, if it's imported by another Python file, then it's going to have the name set equal to the file name. So in this case, this is just shorthand basically for creating another file or calling something from the Python interpreter. And it will, dunder name won't be equal to main, so this executes, and dunder name is equal to pyfile here. Okay. Okay, we also saw the init, dunder init. That's how we assign data to a instance namespace. And in Python, you should know that there are two steps for creating these instance namespaces. The first step is controlled by dunder new. And this method is going to just create an empty namespace, or mostly empty. It's going to add a few things to it. But then dunder init is where we actually add the data that we want to add to it. Okay. So most of the time you won't need to use new, but if you see it, I want you to know what it's doing. One use case for it, if you're trying to implement what's known as the singleton pattern, and in that case, you have a class that can only ever have one instance. And so you might use dunder new to check if you've already created an instance and you're storing it somewhere in the class namespace, and then you just return that. Okay, so let's use some of the other dunders. In this case, we're going to define a class called color, and this is going to be a container for an array or a list of length 3, which is an RGB value. Okay, so what we do is we define our dunder init. In this case, we want RGB. We're going to convert that to a NumPy array. We're going to assert that it has a length of 3, because we're not going to handle transparency here. And then all of the values should be less than, excuse me, should be less than 256. So we'd assume the values go from 0 to 255. Okay, now we're going to implement dunder add. And what this is going to do, well, can anyone guess what this is going to do?
Creating another instance.
It does create another instance, yeah. But because it's a dunder, it tells us it's something special with the Python language.
How to handle addition.
Exactly. Yeah, so formally this is known as operator overloading. And this is how we overload the add operator. So if we wanted to define 2 of these color instances, we'd say color, and this one will be all zeros, and then this one is 100, 100. We're going to add them together. And because in add, we're basically just taking an average and returning a new instance of color. When we add them together, that dunder add is going to get called, and whatever it returns will be assigned to color 3. And then we can just assert that the values are as we expect, 50, 50, 50. Okay, there's a whole bunch of these. There's probably more operators than this even in Python, but these are the ones that that I readily found. So we have a few of the exotic ones. Python, of course, has 2 divides. There's true divide and floor divide. Floor divide is 2 slashes, whereas true divide is just 1. Floor divide will basically always return an integer. There's these bit shift operators. So greater than sign or less than. We have bitwise or, and there's an invert, the tilde. Okay, so another example. This is just, kind of a silly example, but we're going to have a string that implements its own padding. So we define dunder init. We're going to give it a starting string. And then when we right shift it, we're going to add space equal to the number of right shifting to the start of the string. When we left shift it, we'll add the space to the end of the string. And this here tells us that whenever we try to convert this class to a string, that's how we do it. So that makes it easier to print. Okay, so we create an instance, and then we use our silly bit shift operator here, and you can see what it prints out. So the first one has 3 spaces, 6 spaces, 9 spaces, and then this one actually has 10 spaces to the right. We just don't see them. Okay. Okay, getters and setters. Before I move on, any questions about any of this? Operator overloading, some of the how to use the dunder? Yeah.
So can you overload a bitwise instructions as well?
Yeah. Yeah.
XOR or?
So formally, like this invert is a bitwise invert. This or is a bitwise or. There's an and. That one's not listed here, so there's one that I forgot. Bitwise and. And in fact, NumPy does that, right? It overloads the bitwise operator for invert, and then if you have a Boolean array, that will just flip all the bits from 0 to 1. Yeah. Okay, so getters and setters. Sometimes when you access an attribute, you might want there to be some kind of side effect. So you might be dynamically fetching a value from a database, for example, or when you set something, you might have to update other attributes that are related. And so getters and setters come in handy for that. For a simple case though, if you don't need any of these side effects, don't bother with it. You just would say instance.data equals your data, okay? When you need more logic, you go to the getters and setters. If you need to implement a lot of getters and setters, there's something in Python called descriptors, which we don't really have time to cover, but that's a special kind of class that allows you to reuse getter and setter logic. And then if that doesn't work or fit, it's kind of your last option is just to name a method, get whatever and set whatever. So let's look at two examples. In this case, we're just going to use methods called getX and setX. And this will be our class name will be dynamicx. So we could, of course, pass in data to set to the self instance. We're not going to do that here. We just set it equal to none. And then we can call get and set. And then we'll have these side effects of printing these strings. Now, if we want to use getters and setters, this is how you do it. You would say that, so this one has an attribute named y. And so you have this at property and then a function named y takes in the first parameter itself. So this is a method, right? And then it will call print getting y and then return self dot underscore y. And so let's see how we'd use those. So the one where we have just the methods named get and set looks like this. It's pretty much what you'd expect. But when we're implementing getters and setters, when we do dynamic y dot y equals 42, that is actually going to call this function and then return whatever this returns. So it looks like it's a static attribute, but it's actually doing more than just that. Same thing. Sorry, so that would have called the setter. So that would have called this function here. And then when you access dynamic y dot y, that calls this function. Okay. Hafiz, do you have a question?
I'm just trying to understand.
Okay.
So that y dot setter, so that y has to be the same as the function.
That's right. Yeah, it's just kind of a quirk. I'm not sure why it's that way, but
Is it the app property that makes it like getter?
that's right.
We can save the typos.
Okay, so here's an example of when you might want to use this. We're going to implement a class called clock, and it just has one property called time. And so whenever we say clock.time, we want it to return the current time. Okay, so we start by creating an instance, which we call clock at line 1. And then time 1 is going to be equal to clock.time. We'll sleep for 1 second. And then time 2 is clock.time again. Okay, and if we print these values, even though it looks like we access the same data, it's actually different. Because each time we've said clock.time, it's calling this function. Okay. Okay, so inheritance, we've already kind of touched on it. So it's this idea of a directed acyclical graph where we go from the instance to its parent class and then up to that parent class and so on. But Python actually implements something called multiple inheritance. So rather than just having one class here, we might have another class. And this one could have 3 parent classes. All right, so if I do Bob dot some attribute, where should I start looking? It's kind of a problem, right? Because it can branch any direction. So Python has what's called the MRO, the method resolution order, and that's just another dunder. So the rules get really complicated, especially in this sort of situation. So I don't try to memorize them or remember them. If I'm confused about it, I just check dunder MRO, and it tells you as a tuple, I'm going to go first here, 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 and so on. So an example, everyone has maybe seen the pandas library, right? Very convenient for working with tabular data. if we look at the class data frame, so the class name data frame and its MRO, it tells you it first has this data frame. So it's going to look in the class namespace first, and then that has a parent generic ND frame and so on. And what you'll notice in Python is at the top of all of these is going to be this class object. That's kind of like the primordial parent in Python. That's where everything stops. Okay, what's interesting here though, this does have multiple parents. So it has this generic ND frame, this base pandas object, that's all one line. And then we see this dir names mixin and indexing mixin. So what mixins do, this is kind of a sane way to handle multiple inheritance. They should be classes that are like a little bit different, that you're not going to have clashes with namespaces. So I'll show that in a second. Mixins. So the idea here, if we have a class named animal, and then we have our dog, which inherits from animal, and then also this mixin, which we'll call pickleable. So in Python, there's a way to save data as a pickle. It's fairly easy. It's not a secure way to save an instance or a class, but it's used fairly often. What this mixin will do is it just adds this toPickle and fromPickle method. And these should be, there's a mistake here, these should be what? What kind of methods should these be?
Instant.
They should there, if it was an instance method, it would have self as the first name. These actually should be static methods, right?
If it's two different static, then you use the two people, then how you got access to the instant.
Yeah, in this case, you would have to define the class. So the mistake here really is it should be a class method with CLS as the first parameter, and then you just instantiate it with that class. Okay, so let's talk really quick about super. So in this case, we're going to implement a rectangle, and then we have a square. In our rectangle, we have a width and a length parameter, and then we have an area method. So that makes sense, right? And then we're going to go from more general to more specific. That's usually how these class hierarchies work. And in the case of a square, it's a subset of a rectangle, but we only need the length because the width and the length are equal. But if in this init method, we want to call something from one of the parent init, in this case, the direct parent, we can use this keyword called super. And so when we initialize a square, it goes here, it has length, and then it's going to call init on rectangle, passing in length and length. Okay. Aaron, any questions there? Okay. Okay. All right, so this is how we check for if something is an instance or a subclass of something else. So we have our parent and our child class. We'll instantiate child and say, is instance child child? Is that going to be true or false? Should be true. What about this one? Should this be true or false? What do you think, Adesh? True? Yeah. And it's not its direct parent, but it is in its MRO. So that is going to return true. Okay, how about this one? What do you think, Payam? False. It's a trick. Child, capital C, is not an instance, it's a class. So is instance is going to say false. But if we say is subclass, that's true. Now this last line, line 12, if we ask is subclass with something that's an instance, this is actually going to raise an exception. I would prefer it to say false, but it doesn't. Okay, so is instance checks. This is going to be important if you're trying to figure out what an object is or what it behaves like. Let's talk just for a second about data classes. So this is a very convenient way to automatically create a lot of these Dunder methods in a sensible way. So imagine you have a piece of data. In fact, I have an example here. So let me just go through a few things you can do. It automatically creates these Dunder methods. You can specify if it's frozen, which means you can't update it or change it. You can also control input modes, like you can specify you have to use keywords. So when you initialize it, you could say, instead of saying 42, this would raise an error, you'd have to say data equals 42. And in some cases, this might be more clear because you can, when you're just passing in the parameters in an order, it can kind of get confusing. So these are some things you can do with them. Let's make that more concrete, look at an example. And this one's for you, Gwen. So we have an ocean patch, okay? And I'm envisioning this to be some kind of volume in the ocean. And what we're going to do is set time. So maybe this is part of a simulation. We have our dimension. We're going to assume it's a square, so we only have one dimension. And then we'll have some kind of velocity vector and some temperature. Okay, so we have to have this Dunder init method. We have this Dunder stir method, Dunder equals. You can probably guess what equals does. And there might be even more we have to implement for this sort of to behave nicely in an intuitive way. But if we want to use a data class, this is all we have to do. So we just import data class from this data class module, and this is in the standard library, so it'll be in any Python installation. You add this @data class above your class definition, and then you say ocean patch and tell it what pieces of data it should accept. And so in light of what we were just talking about, this is a little bit confusing because these would all look just like class data on the class namespace. But because, again, we have that @data class here, this is kind of shorthand for what I just showed before. Okay, any questions on data classes?
You have to define the type.
What do you mean by that?
So can I just have time? It can be in the row.
Why is the type hint here?
Right.
Yeah, good question. So you do have to define the type hint. It's actually not used for anything. It's just to inform the data class that this is going to be part of the input parameter. So that's a little bit confusing.
So well, we won't raise exception.
No.
If it's
Yeah, you can write anything you want there. If
it
you
has
use,
to be a predefined, right? So it cannot be ABCD.
actually, if you have from Dunder future import annotations, the annotations are delayed. So you could put anything you want there, even if it's not defined. But you shouldn't do that, obviously. If you want these types to actually do something, there's a library called Pydantic where it will actually make use of them. There's another library called Adders as well that does something similar. Okay, so last section here is protocols. Yeah, Hafiz.
So does this,
Next one, this one here.
does it take care of just the dev inits, or does it take care of other?
It does quite a lot. And in fact, in this data class, it's a, yeah, so when you call @data class, you can have open paren, close paren, and specify what you want it to do. But by default, it will do things like Dunder stir, Dunder equals, Dunder init, Dunder sort, I believe, or Dunder less than, Dunder greater than. There's a few that are associated with sorting.
Whether you can define more methods under this.
Yes, you can. Yep. Okay, so last topic here, we have 5 minutes left, is protocols. And this is a little bit more advanced, so I want you to be aware of it and be able to remember it in the future if you need it, but you might not need it right now. This would be more like if you're working on a library or something. So in Python, protocols is, this idea is kind of built into the type system. And it's a way to say we have a specific type that behaves in some way rather than actually checking if it's that type. So this is related to the idea called duck typing. And if you look at a duck and it quacks, it looks like a duck and it quacks, it's probably duck enough. We don't need a sequence to DNA, right? This is the same idea in Python's type system. So you use Dunders to implement different protocols. And there are any number of protocols that can be defined. There's some that are built in that I'll show you, but you can define your own protocols as well. So here's some common ones. We have a sequence. A sequence just means that there's some kind of data that can be placed in order. Mapping behaves just like a dictionary. A dictionary implements the mapping protocol. Collection, hashable, reversible. There's quite a few of these. I won't go through all of them, but let's look at some examples. So we create a new class and we call it sized thing. And how we would use this is, well, first of all, we would define this dunder lane. That's going to implement the size protocol. And then from the typing module, we can import sized. We initialize an instance of size thing. And then we will just in line 5 say, is this an instance of sized? Okay, and this gets confusing because nowhere in line 1 did we inherit from sized. But because it implements the protocol, that is, it has a dunder lane method, it is considered an instance of sized. It behaves like a sized thing. Okay. So that's one of the simpler ones. Another simple one is hash. So if the class implements a hash method, that means it can be used as a key in a dictionary, or it can be placed as a member in a set. It's hashable. And so we do something very similar here. We would just import from typing, we'll import hashable, create an instance, and then we can use our instance as a key in a dictionary now. Okay, here's an example that you were asking about, Hafiz. Can we add additional things to data classes? And here we add a call method. So we're talking about how in Python, the call operator means open parentheses, close parentheses. So in this case, we can instantiate it. So we create an instance with the call from my callable class, but then we can also call something. So my callable instance, and we pass it -1, and then that will call this dunder call method. Okay, so there's two ways to define protocols, and you might do this in a library. For example, in DASCore, we have this object called a spool. And the idea is it behaves in an abstract way such that it can manage different data sources of DAS data. So it doesn't matter particularly what the data source is, but it should have similar methods so that the user doesn't have to know what kind of spool it is. They might be pulling data from an online resource, from data that's already been loaded into memory, or from data that's saved in a directory. It's all going to behave the same because it implements the spool protocol. Okay, so we do that with the ABC module, that stands for abstract base class, or we can do it with protocol from typing. So let's look at some examples and I'll show you what this is talking about. So if we want to define a protocol with ABC, we'll define a deck. This is going to be something that we can shuffle and we can draw from. It might look familiar from the exercise for style. And so what we say is we inherit from ABC. We have an abc.abstract method, and that's saying in order for a subclass of this to implement this protocol, it has to define this method. If it doesn't, you won't be able to instantiate it. So here's a concrete definition or a concrete class of my deck. So we're going to inherit from the deck ABC, and then we have to implement these two methods. And they have to have the same number of parameters, and they might have to have the same names, I forget. But here in line 19, if we hadn't done it correctly, this would raise an exception and crash the program. So that's how you know you've implemented the protocol with an ABC. For typing.protocol, you simply inherit from protocol again, and you can add this @typing runtime checkable. So normally this is for like static type checkers, but if you want to do runtime type checking, you can do it this way. And then rather than inheriting from that, like we did with the ABC, basically you can just check, hey, is this thing that I have created, is that an instance of my protocol? And if it returns true, you've implemented the protocol correctly. False, it's not right. Okay, so let's wrap it up. Object-oriented design, there's a few advantages. We talked about how it can be expressive, it can create intuitive interfaces. You saw how you can add vectors together and things like that. You can have this modularity or extensibility through inheritance, which is quite useful. And it's a common paradigm. There's a lot of object-oriented programming languages. Some of the disadvantages, it can be overly expressive and sometimes give you too much freedom. A lot of times you can end up sharing too much state, which makes it hard to debug programs as well as parallelize them. And you can have slower execution. So if we created a bunch of objects versus using NumPy arrays, that's going to be much slower, especially in Python. Probably some others, we're running out of time. So here's a good example of object-oriented design. We start with something abstract, some abstract animal, and then we have a person, and we have a pet, and then we have these sort of concrete classes called dog and cat. So this is how it's supposed to work. Oftentimes it ends up looking like this though. So this is when object-oriented design sort of explodes in complexity, and it may not be a good idea. So good examples in Python: Pathlib, Pandas data frame, scikit-learn has a really great object-oriented API. Pydantic has a good one. In Pathlib, before Pathlib, you had to do this mess with os.path to join strings together to behave like paths. But now with Pathlib, you can just divide them, right? It looks like you're adding strings together. So data path slash the facts.csv, that creates a new path, and it just does the right thing on all the operating systems. It was very handy.
Why is TY not plus?
Why is it not plus? Because they're not strings. This is a path object, and it overloads the divide operator rather than the add operator for
Right,
add.
no, I just wonder what the logic.
It looks like
It
looks like a path. Yeah. So it's intuitive to use because we're already familiar with that, right? Okay, there's a few dreaded ones. A lot of these are like thin Python wrappers around libraries that are written in other languages. So PyQt, VTK, these are C++ libraries, and there's just like so many objects. It's hard to even use the library. You have to memorize at least like 10 different objects to use it. Boto3, this library kind of interacts with Amazon Web Services, and it does a lot of dynamic class definition and loading. So it's kind of hard to figure out what's going on because there's so much dynamicism. So finally, my guidelines, free advice, take it for what it's worth. When you're designing an API, common use cases shouldn't require more than 3 classes. Otherwise, you're really building a puzzle. You're not building something that's really intuitive. Classes are simplest when they're extensions of familiar protocols. So for example, in ObsPy, the stream object behaves like a list, plus it has some other methods attached to it. So you start with something you already know and add a little bit to it. Class division should be at a high data level. So you would want to, for example, create a data frame which manages NumPy arrays rather than try to have every row be some kind of object. So if you're creating millions of objects in Python, it's just going to be slow. Take it easy on operator overloading. You might think this is really cool. I can do all sorts of crazy things with it like we did here, but it's usually not a good idea. And then avoid deep and multiple inheritance, except in the case of maybe like these sensible mix-ins. Prefer to return new instances rather than modifying data in place. And lastly, functions are just fine too. You don't have to make everything a class. Okay.
The second to last item. So I always wonder what's the, mind side behind it, because it seems to create a lot of redundancy for that.
Well, it could create redundancy, but imagine like in the case of DASCOR, we have an array that's right. It's read-only, it's immutable. So when we return a new instance, we can actually have a copy of that array because the instances can share it because no one can change it.
So, but for example, in your, processing in the task or in the processing module, that each time you bypass filter it, you actually create a new data array.
Yeah. Yeah, and you have to do that anyway for NumPy. But the problem is, so if you had var1 and this equals, I don't know, data class, and then you have var2 equals var1, and then we have, let's call it filter, equals var1 dot filter. If you change this in place, everything that was using var2 isn't expecting to see that change. Right, so
Right.
downstream, if this modifies its data in place,
Mhm.
downstream, you can have bugs that would be hard to sort out because you don't know when this would have
Yeah.
changed.
Right.
So that's kind of the rationale behind it. Any other questions? Hopefully this all makes sense. I tried to blend it as like a gentle introduction and also give some more advanced features that might be useful. So, but yeah, feel free to come talk to me if you have any questions. And next week we'll cover functional programming, which is kind of a whole different paradigm.